time. We're done Kirchoff's current law, so I guess we better start on the voltage law now. The rest of the questions, for those who haven't finished them, the stuff you can have a go at in between time. Kirchoff's voltage law. KVL is at any instant in time closed loop I'm going to put any closed loop actually sum of all the voltages volt drops. I'm going to put actually volt drops and sources of voltage equals 0. At any statement in time, in any closed loop, yeah, I changed my mind. I wanted to put any closed loop because you can have multiple loops in a circuit. The sum of all the voltage drops and sources of voltage is equal to 0. So, what we're saying here is, if we have a circuit like so, and the source like so, current wise we might, I'll come to that as go shortly. We've got currents flowing in all these legs. We'd have E1 there, let's say V1, V3, V2, for instance. Okay. Sources E1, for instance, yeah. Voltage arrow in direction of current. So I'll put the current flowing up, yeah, away from, let's say, the positive terminal of that battery or source or whatever it is, and it's in the same direction. The voltage arrow across it is in the same direction as the current flowing. For volt drops, V1, V2, V3, V4 in the case of this circuit. Yeah. Voltage arrows. Point opposite the current flowing through. It's important that we label up correctly like that when we come to formulate our Kirchoff's voltage law equations. So for the volt drops, I've put all the arrows going against the indication of the current flow, and so in this video we've got current flowing left to right, so the voltage arrows right to left. This one's right to left. This one's up because the current's going down, and so on. Yep. And in this circuit we've got, remember the statement said, in any loop at any instant in time. So we got one loop there. We've got a second loop but we've also got, even though it doesn't include any sources, we've got a third loop around just those three resistors. We could use any of those three loops for the Kirchoff's voltage law equation to solve problems. Yep. It's any complete loop or path for current in a circuit. Any alternative one could be chosen. Okay, it's a bit muddled, that diagram, but indicates what the law is all about. Yep. We'll come on to that in a minute, but it's the fact that it is a loop. Yep. All right. I knew there was something I meant to do. I meant to copy that black circuit drawing before I wrote all over it, but never mind. Okay. What we do is so when we want to create our equations, it's a little bit like we did for the currents. For a particular loop, put clockwise arrows of clockwise voltage arrows. Left hand side, anti-clock arrows. Right hand side. So for loop A, we'd have clockwise arrows E1, it's the only one, anti-clockwise arrows equals V1 plus V2. That would be loop 1. So if we knew any two of those voltages, we could find the third one. For loop B, again, this is the one all the way around the outside. We've got E1 is equal to V1, V3 and V4. And then lastly, for this loop B, loop C, sorry, the clockwise arrow is V2. And that's equal to V3 plus V4. So from those three equations, why? We're talking about that loop. This volt drop here, V2, is the source to those two resistors, regardless of what. But, yeah. This voltage here must add up to those two. That's the law. Yeah. So you can pick any two. So if I value and one of the other three, you could find something else, because you could use that last equation to find V2, and then if you had E1, you could then use either of the other two equations to find V1. All right. So that process, a bit like with the currents, of making sure the most important thing is putting your arrow, labeling that diagram up with the arrows in the right direction. Yeah. So this bit, the arrows go with the current on sources against the current on loads or resistors, and then we put all the clockwise arrows one side, all the anti-clockwise arrows the other side, with an equal sign in the middle. Rearrange as appropriate to find the unknown. Examples. Oh, hang on, got another resistor down here. Okay. So we've got, what unknowns have we got in this circuit? V2 is an unknown, V3 is an unknown. What loops have we got? I, B, and C. by Kirchoff's voltage law, loop A, E1's the anti-clockwise arrow, is it not? Yeah. Is equal to V1 plus V2 plus V4. That loop there. The unknown in that is V2. So V2 is equal to E1 minus V1 minus V4. It's 50 minus 10 minus 20 equals 20 volts. Yep. Loop B. E1 equals V1 plus V3 plus V4. I heard someone say that's the same. Yes, it is. Okay, what I'm going to try, I'm doing to you, is proven that all the loops agree, because that's what the law says should happen. Alright, so we want to find V3, so V3 is equal to E1 minus V1 minus V4. That is 50 minus 10 minus 20, 20 volts. Finally, we've got a loop here with two resistors, and by Kirchoff's law, the clockwise arrow V2 is equal to the anti-clockwise arrow V3. Therefore, V2 equals V3. And the point there is, the extra loop is a check. All three should concur. Yeah, all of them should follow the law. And so as first one, make sure that all, and it's proof that the voltage across these two resistors in parallel are equal to each other. Kirchoff's voltage law proves it. Alright? Right, we'll just have a look at one more example. Okay, and this one's one where we got more than one source in it. So, there's your circuit. I'm going to put some voltage arrows on. So this is E1, 10 volts. Voltage arrow that way. E2, 20 volts. Voltage arrow that way. E3, voltage arrow that way. Now, given the information so far, which way would you put a current on that diagram? Can we're going to put a current arrow on it that way. This is an example of where we made an arbitrary decision, really know what direction it's going in until we know more information. Yeah? So having done that, we can then make that V1 and that V2. £30 and 20 volts. Again, if you weren't sure about voltage arrows, if you get a negative voltage, then you put the voltage on the wrong way. It's the same as you can try something. The unknown here is E3. So you go ahead and you use the rules with to do a Kirchoff's voltage law equation, where we put the clockwise arrows, which are E1 plus E2 on the left hand side, and the anti-clockwise arrows E3 plus V1 plus V2 on the other side. And then that's E3 we want to find. So that rearranges to E3 is equal to E1 plus E2 minus V1 minus V2. Then we put the numbers in. E1 is 10 volts plus 20 volts minus 30 volts minus 20 volts. Yeah. What that means is that's actually, yeah. Okay. Yep. Minus 20 volts. Because always remember, that's in time. And where you could see, give me a basic example of where you could see current flowing into a source. Charging a battery. Yep. So that's an example of, you've got a source, a battery that's low, and you're sending current into it to charge it back up again. Opposite to the normal polarity. Okay? So in your, you've been given Kirchoff's voltage law equations, and this is what I always put up for you to have a look and think about. So I'm going to put another one up there for people like Lewis who do things really quickly, and one that's quite a common thing, a circuit that you would find in instrumentation. Yeah. So the square of three resistors of all equal value and a resistor Rx across the middle, 10 volts. How much current flows through the resistor Rx? But have a look at the other questions first. And then the last 5 minutes, I'll go through that anyway. Right guys, let's just take a look at this circuit here. There's the real world circuit. Don't really need to put a voltage on it, but I'll put one on. It kind of makes it a little bit easier. If we start to apply current arrows here, we probably do that because we're going to put a voltage arrow that way. And then when we get to this node here, we're probably going to say there'll be some current go down that one and some current down that one. When we get to this point, these 2 points down here, we're obviously going to get some current flow down there because eventually it's got to go that way. We're also going to get some current down there because that's got to go that way as well, and those two currents add together. We could argue there's a current flowing that way from what's coming down here. We can argue there's some current flowing that way from what's coming down there. Alright? But the easiest way to see this is to look at the voltage arrows. So, current's going that way, voltage arrow that way. Current down, voltage arrow that way. Current down, keep to my colours, voltage arrow against, voltage arrow against. Now, looking at this loop around there. So up there, through those two resistors, forget that one for a minute, because there's a complete loop from there, down there, through that resistor, down through here, back to there. E1 is equal to ER, call it R1 for the sake of argument, ER3, even though that, no, that'll be true. So if that's 10 volts and those two are equal value, what are the voltages, ER1 and ER3? Volts, because those two values are equal, the resistor values are equal. 1 equals R. Five volts there and 5 volts there. Applying the same logic to this loop all the way around the outside, we'd have 5 volts and 5 volts there too. Everybody follow? Yeah? So, if we then look at one of these loops around here, we got a clockwise arrow of 5 volts, an anti-clockwise arrow of 5 volts, and then we got a question mark arrow here. And those three have got to add up to nothing. So if we got 5 volts on one side and 5 volts on the other, whichever side I put VRX on has got to equal 0 for that to be true. So if there's no voltage across a resistor, how much current flows through it? By Ohm's law. Yep. That circuit is a weak stone bridge. Yep. And it can be used in instrumentation, particularly with strain gauges. So a strain gauge, modification to it. So what they do is just quickly draw the bridge again. And in fact, it will do its business as long as these two resistors are equal and these two resistances are, so they don't all have to be same value. Now, they might well have a resistor in the middle. The idea being, when that, if these two are equal, okay, when R3 is equal to R4, zero current in the middle, that means it's balanced. Yep, so you'll set that as a 0, okay. Then what happens is, instead of one of these legs being a resistor, you'll put a sensor in there that varies resistance. So a variable resistor, draw a variable resistor symbol, and I'll show us on leads. So that's a strain gauge. Or maybe an RTD to measure temperature. RTD is a temperature sensing device that changes resistance with temperature. Although you'd have to be a bit careful because you're actually heating the sensor up by passing current through it, so it's not the ideal way to do it. So what you're doing now is you've got your strain gauge in here. As you put weight on it or take weight off, it's going to vary resistance, and a voltmeter across there will see a deflection. What they'll actually do is amplify that signal, because you tend and you get facing by putting a resistor in here, and what you normally use is like a decade box resistor, but another variable resistor, but a fixed value. So like switches with thousands, hundreds, tens, 0.1, and you resistance step. You connect your unknown resistor here, and then you vary that until it's balanced, till it indicates 0 in the middle, and you then know two are equal value. So the value that comes from your unknown resistance is equal to the value. Alright? Use a meter with a gauge that's actually measuring voltage, but you'd mark the scale, mass, weight, or whatever it was if you were doing straight, if you were doing 10. What is it? What you're using is a 0 cent, probably 10 to 0 in either direction. Instrument. It's worthwhile doing a little circuit to prove that all this stuff we talk about is important. All right.